we shall look at other existing architectures which can help us in solving this problem. The very first one is the long short-term memory architecture, which is made of long short-term memory cells as its basic unit. LSTMs help us solve the problem of vanishing and exploding gradients. Let's see in detail how the vanishing problem comes about when working with the naive model of the RNN, that's the basic RNN units we had seen previously. Previously, we had shown that the partial derivative of a hidden layer with respect to a previous hidden layer is given as the product of these two matrices, where I is given from k plus 1 to t. So we're moving from, say for example, this hidden layer to this hidden layer where we have t equals 4 and k equals 1. We're moving from I equals 1 plus 1. So we're moving from I equals 2 to 4. And then we're multiplying this, or we're finding the product of these two matrices as we go ahead. And as we go ahead, we're able to calculate this partial derivative of hi with respect to its previous hidden layer. Now, let's define the L2 norm of a matrix A, whose row and column is governed by ij, where this L2 norm is the sum of each term that makes up A squared and all of that square root. Now, we have the L2 norm of this matrix, that's this WHH matrix transpose, which can be less than or equals a constant alpha. So right here, we're supposing that when training our model, we may arrive at a point where the L2 norm of this matrix has a value less than or equals a certain constant alpha. So it never goes above this constant alpha. Now, looking at this other matrix, this diag of A1 prime of HI minus 1, we could also say the L2 norm should be at most better. So here we have these two matrices which have maximum values alpha and better for their L2 norms. And then when combining this, we have that the L2 norm of this by this now is always less than or equals alpha times better. Since the L2 norm of this matrix times this matrix, that is actually having this times this and finding the L2 norm, is less than or equals the separate L2 norms, we could confidently say that the L2 norm of H with respect to its previous H is less than or equals to alpha times better, since we had right from here that this is equals this. And then obviously the partial derivative of ht with respect to hk, that is a layer far from this layer ht. In this case, for example, we had seen that k is equals 1 and t equals 4. So this partial derivative, as we have seen, is a product of this partial derivatives of hi with respect to hi minus 1s. So that's how we have that the L2 norm of this partial derivative is equals the L2 norm of this product. And then from here, since we had this relationship already, we could clearly see that this L2 norm is less than or equals this. So right here we've replaced this with alpha better, and now we're left with the L2 norm of the product of constants, which is equals basically the constants. That's the product of the constants. And then from here we simply find the product of alpha better. Now multiplying alpha better times alpha better times alpha better, t minus k times, we obtain this. So to move from k plus 1 to t, we go through it t minus k times, and that's how we obtain alpha better to the power of t minus k. And so from here we see clearly that this L2 norm is less than or equals alpha beta to the power of t minus k. So in a case where the partial derivative of this ht with respect to hk is maximized by a certain alpha beta to the power of t minus k, then it happens that if alpha beta is less than 1, that is, more precisely, if alpha beta lies between -1 and 1, so here we have a value which lies between -1 and 1, then taking that value to the power of a positive number will give us a value which is very small. Now, suppose we have a very large network where we have 1,000 of these LSTM, or rather of these RNNs, which are stacked. In that case, when calculating this partial derivative of ht with respect to hk, we shall have that if t equals 1,000 and k, for example, equals 1, then t minus k is 999. Then right here we shall have alpha beta to the power of 999. Then the L2 norm of this partial derivative will be less than that value. And in that case, we shall have, suppose alpha beta is, for example, 3/4, or any number between -1 and 1 to the power of 999 is almost 0. So this tells us that this partial derivative wouldn't change much. And so generally when training RNNs, we have to struggle to make sure that this L2 norms, or this L2 norms of this matrices WHHT and then this diagonal matrix, don't actually become too small. But in practical or in real life problems, many times they actually have values between -1 and 1. And in that case, you shall have the vanishing gradient problem, where we can't update our model very efficiently since these gradients are practically 0. And that's the reason why we study models like the LSTM, or models like the LSTM we actually built, because with these models now we could try to solve this problem of vanishing gradients more efficiently. So with this, we've seen in depth how the vanishing gradient problem comes about, and now let's see how to mitigate these problems using the LSTM networks. The RNN model, as we've seen, is not the best suited model for handling long-term dependencies. This simply translates to the fact that after stacking up many RNN cells together, and so for example, if you have RNN cell 0 and another RNN cell 1000 with 999 RNN cells between these two cells, we have that the cells somehow lack communication, or there is little transfer of information between the cells, of which, as we know very well, the RNNs are meant to solve problems where the input data has parts which are related to each other over time. So to solve this problem with the LSTM, that's the long short-term memory network or model, which too is composed of an LSTM cell as its basic unit, we introduce a cell state. So right here we have a cell state, and we also have the hidden state. So we have the input X, we have the cell state, the previous cell state, the previous hidden state, and then the current hidden state. And then we shall include other gates which will help us store information in the cell state or remove this information in the cell state, depending on how important it is for other LSTM cells. So unlike the RNNs where we didn't have control of the amount of information to be stored at a given state, here we have, or we try to get as much control. So that's why the LSTM solves the problem of handling long-term dependencies. Let's dive deep into this. So suppose we have this input X, and then we have a previous hidden unit and this previous cell state. We concatenate the input with this previous hidden unit and then pass it through a neural network, which has as activation the sigmoid function. And the sigmoid function, as we know, outputs values between 0 and 1. So if we have an output right here which is 1, it simply tells us that information coming from this previous hidden unit and the input unit shouldn't be forgotten. Now if this outputs a 0, it means all this information should be forgotten. So basically right in this block we have a simple neural network, and then here we have pointwise multiplication. So once we have this previous hidden state, we have pointwise multiplication right here, and this ft is the output of our forget gate. Now we move to the next. Right here we have an input gate. What the input gate does is very similar to what we just had here with the forget gate. We have this neural network which is completed by a sigmoid activation function, which gets its input from the concatenation of the hidden or the previous hidden layer and the input layer. So that's what we pass in here, and then we get the output it. And then also with this we have this other gate which gets the same inputs and then completes with a tanh activation function, hence this T symbol right here. So once we complete this, we now do a pointwise multiplication of the two outputs we have right here. Let's denote this output as dt. So if we have this pointwise multiplication, we now pass this as input right here, and we have a pointwise addition. So now notice that with the forget gate, we decide what information is to be forgotten or what information do we let go. And that's why we have a pointwise multiplication here. Whereas with this input gate, we decide what information do we add to this R cell state. So by having this addition or this pointwise addition, we are capable of adding information into our cell state. And with this, we obtain the output cell state or the current cell state from the previous cell state. So this shows us already how we use the forget and then the input to manipulate the kind of information we have in this cell state. And then we look at the output state, which is clearly the output from this output gate. The output gate is very similar to this too. Here we have the sigmoid, we have a neural network, which from here outputs this OT. And by doing a pointwise multiplication with the output from this activation of the CT, we obtain the hidden unit HT. So again, this output gate controls the information we output from this cell state. Note that right here we just have an activation and there's no neural network as compared to this 4 other gates. So from this, let's put down some equations. We have Ft, which is the sigmoid of WF. WF here is the weight matrix of the forget gate. So we have this weight matrix multiplied by concatenating the hidden state previous and the current input unit xt. So when we concatenate this multiplied with our weight matrix F, that's WF, and then add it up to the bias BF, that's the bias of the forget gate, and then finally apply the sigmoid function to give us F of t. And then to obtain I of t is similar. We have WI, that's the weight matrix of the input gate, and we have BI, the bias of the input gate, with the same inputs, which is the concatenation of HT minus 1 and XT. And then we move to DT. DT is the output get right from here. So DT is a tanh, that's the activation function now is a tanh. So tanh of WD, and BD. Then from here we have OT, which is the sigmoid of WO, that's the weight matrix, times the concatenation of this, plus BO. And then from this we could obtain the cell state at time t, which is FT times, that's a pointwise multiplication, FT times CT minus 1. As we could see, it gives us the ability to forget information or let information pass, plus dt times I of t. This other one gives us that possibility to add information to our state or not. So that's how we obtain CT. And then HT, which is the hidden state, is O of t times tanh of CT. So this is the tanh of C. This is the tanh of CT, which is the output here, times O of t to give us H of t. Now note that with the LSTM unit, HT is the same as the output. So this HT is the same as YT. And so unlike the RNNs where we had just HT minus 1, XT, HT, and then YT, now we include this cell state, which permits us either forget information, include information, and also to output information. Now note that LSTMs don't come to completely take away the problem of vanishing gradients, but they help a great deal in mitigating this problem. That's why it's one of the most popular recurrent neural networks used in practice today. Talking about LSTMs in practice, an LSTM layer is formed by stacking this LSTM cells together like this. So right here we have the input hidden unit, the cell unit, and then we have this output hidden unit and output cell unit. Recall that this output is the same as this, and then we have this input. So we simply repeat this L times, since our sequence length is L, that's the number of LSTMs we stack is equals L. So if we have an input with shape, batch size, sequence length, vocab size, then the output will be of shape, batch size, sequence length, hidden unit size. So instead of having the simple RNN, we shall replace this now by an LSTM unit. So let's have this LSTM. We could import from this. So we import the LSTM, run this. We have our LSTM right here. Okay, so we could take this off and run that. So here we have the batch size, we have the sequence length, and we have the vocab size. We shall see how this is going to be turned into the batch size, the sequence length, and then the hidden unit size. So which is basically in this case 4. So we could say we'll put this to a value like say 40, and then right here let's take this off. We have the return sequences, and then return state, which for now let's let it to be false. Okay, so that's it. So we have this layer, we have now the inputs, and then we'll pass it through the layer, and let's check on the outputs. We'll see that we have now an output which is of shape 8 by 40, and that's because we are getting just the last LSTM cell. Now if we have return sequences to be true, we'll see that we get all the LSTM cells. So that's why now we have this sequence length which is included, and with a 40, since that's our hidden unit size. Now let's say we have this return state to be true. So you see that there's an error, because when the return state is true, we are not only returning just the outputs, but also the hidden states and the memory state C. So right here we should have outputs 0. So let's just repeat this. We have output 0, output 1, and output 2. Here we have C. C, which is actually the memory state, and this is H, which is the hidden state. And this is the usual output. So we can run this and we see now that we have the usual output, we have the memory state, and then the hidden state. And take note that this is the memory state and hidden state of the last LSTM cell. So that's why we don't have a sequence length in the output shape. We can now replace this simple RNN with the LSTM. So right here we have LSTM, run this, see our model. We then compile the model, and then we could go ahead to train this model. We've had this name LSTM embedding right here. So we shall monitor this time around with a validation loss. So take this and then we'll run it. Now after training for 50 epochs, we have the following results. We see how the loss decreases, the accuracy increases, and then the validation loss also decreases, although at a certain point it stagnates, and the validation accuracy too increases, although at a certain point it stagnates. We then go ahead to produce plots. For this, we see that the loss, as we saw, decreases, stagnates, and then the validation accuracy increases, stagnates. But notice that the highest or the maximum validation accuracy we obtain is the greatest so far. So it's greater than that we obtain with a simple RNN model, as we obtain values of close to 80% in accuracy.